Getting into Space by Alex, Simon, Pasindu and Kaito. The main topics that we will be covering today is the history of space travel, what is space, design considerations, multi-stage rockets, reusable spacecrafts, rocket fuels, and future developments. We are going to start by giving you a brief introduction into the history and background behind space travel. I think it is extremely important to understand the background in order to appreciate the focus of space travel developments today. The history of space travel has been very recent in human history, starting only really with the development of the Nazi V-2 rockets towards the end of the Second World War. The development of space travel itself only started post-World War II and famously led to the space race between the fierce superpower rivals of the USA and the USSR, which subsequently shaped the second half of the 20th century. It is hard to think about space travel without linking it to the Cold War in some way. As mentioned earlier, it was the fierce rivalry between these superpowers that accelerated the development of space travel and led to the USSR's first sending the first satellite, the Sputnik 1, into space in 1957, and subsequently, in 1961, sending Yuri Gagarin, the first man, into space. These events were hugely humiliating for the United States of America, who post-World War II took a much more dominant role in global affairs and its stiff stance against the rise of communism around the world. However, the recently elected and hugely ambitious President John F. Kennedy promised the world that the United States would land the first man on the moon. The Americans finally succeeded on the 20th of July 1969 when Apollo 11 successfully landed on the moon, where astronaut Neil Armstrong famously proclaimed, "One small step for man, one giant leap for mankind." There were 8 further Apollo missions flown after 1969. However, the political gains of these moon landings were becoming less and less significant. Rocket launched around this era were all single-use disposable launches. The idea of multi-stage to orbit rocket worked in the early days where cost was not a concern. However, with the Cold War coming to an end, it was important to find a more economically viable alternative. This is where development on single-stage to orbit spacecraft, and usable spacecrafts, which are the holy grail of space travel, first came into use. The US first introduced the multi-stage space shuttle in 1981, hoping to make space travel economically viable. For comparison, a single Saturn V rocket launch cost $375 million in 1969, which equates to a few billion in today's money, compared with the Space Shuttle's $450 million launch cost in today's money. And now, with SpaceX's latest Falcon 9 reusable launcher, it costs only $5 to $7 million per launch.
What is space? Space is defined as a region that exists between celestial bodies such as the Earth and the Sun. Space is known to begin at 100 kilometers above sea level. This distance is known as the Kármán line and exists well over the ozone layer and mesosphere as seen in the diagram. To get to space, an object must first be able to escape Earth's gravitational influence. To do this, the object must at least travel at a velocity known as the escape velocity. Once the escape velocity is reached, the body has no kinetic nor gravitational potential energy. No further impulse is required by the fuel. The escape velocity can be calculated from the formula shown below, where g is the universal gravitational constant, and r is the radius of a celestial body. M is the mass of said celestial body. On average, the escape velocity for an object leaving Earth would approximately be 11.2 kilometers per second. A rocket works by exchanging momentum with the propellant fuel. The fuel goes through a nozzle at a certain mass and velocity, which helps generate a force to push the rocket towards space. The efficiency of the fuel used is determined by the impulse generated per unit of fuel used. This is known as the vehicle-specific impulse. Other factors that make a good fuel are ignition, combustion stability, temperature, storability, toxicity, and availability. The orbiters need to have a high specific strength and stiffness if they are to withstand the stresses involved in liftoff and re-entry. For this reason, aluminium and titanium alloys are used. Aluminium has a high specific strength and stiffness, while titanium, being heavier but stronger, is used to reinforce certain parts of the orbiter. To resist the alloys from heating up during re-entry, every orbiter is coated with tiles of silica fibers. Silica is an excellent insulator of heat and helps protect the aluminium and titanium components. During re-entry, the belly of the orbiter is the hottest, so the fuels are coated in black glass to help reflect most of the heat back into the atmosphere, while the rest is absorbed by the tiles. The upper region of the fuselage is a much lower temperature, so these tiles are covered by compounds of silica and aluminium oxides.
The majority of the weight of a rocket is the propellant, and when this is burned off, the weight left over is near empty tankage. It makes sense to discard it to lighten the load and allow the rocket to achieve orbital velocity. The term given to lightening the load is called staging. The first type of staging is serial staging, and it consists of a smaller second stage rocket being placed on the top of first stage rocket. The first stage is ignited at launch and then discarded after its propellants have been extinguished, leading on to the second stage propellants being ignited. The payload is carried on the second stage, and it could include a satellite or maybe even astronauts. Parallel staging consists of several first stage rockets, referred to as strap-ons, being strapped onto the central sustainer rocket. The strap-ons are then discarded once their propellants are extinguished. The sustainer rocket engine continues burning once the strap-ons are discarded, which allows the payload to be successfully carried into orbit. This video shows the separation of the 4 boosters on the Soyuz rocket, an example of parallel staging. This is a video clip from the same rocket as before, but this time it shows the separation of the first stage from it. This means that it has parallel and serial staging. Rockets are fin stabilized, which means they maintain their direction of flight by air flowing past their tail fins. To do this, it must be traveling at a speed through the air, such that there is enough force being exerted on the fins to correct the rocket's direction of travel. If a rocket travels too slowly, such as when leaving the launch pad, it may not remain stable. Multi-stage rockets are known for this, because they're so heavy, so it's paramount that the acceleration at liftoff is enough to allow them not to do this. The equation that gives the acceleration at liftoff, which will provide adequate flight speed, is the thrust-to-weight ratio minus 1. It's typically measured in Gs. Static stability is ensured by always having the center of gravity of the rocket ahead of the point at which drag is centered, also deemed the center of pressure. The center of gravity should be at least 1 rocket diameter ahead of the center of pressure. It's important to remember that a liquid-fueled rocket consumes its propellant, and thus the center of gravity will shift in flight.
A space shuttle is made out of 3 parts: the orbiter, the external tank, and the solid rocket boosters. Rocket boosters were initially thought to be reused, but this idea was abandoned due to factors like cost, complexity, and added risks. Instead, a partially reusable design was used, where the orbiter and boosters would be refurbished before being used again. This helps save costs over time. However, the external tanks are discarded after each launch.
SpaceX is a private firm founded by Elon Musk and is at the forefront of reusable spacecraft technological developments. In March of this year, SpaceX made history by successfully landing a used Falcon 9 spacecraft. This breakthrough was revolutionary in space technology, proving orbital rockets can be reused, saving tens to hundreds of millions of dollars in manufacturing costs per rocket launch. The area of technology that we will focus on is the return of the first stage rockets back to Earth. Once detached from the second stage, cold gas thrusters fire to flip it around. Once this is complete, the engines will fire again to bring the speed down for re-entry and give an appropriate trajectory to the landing site. Upon re-entry, the grid fins deploy, which provide aerodynamic control which allow the rocket to be steered. Finally, all three devices act to ensure the rocket lands on the landing barge. SpaceX is not the only private firm looking to build reusable spacecrafts. We have Reaction Engine's air-breathing hybrid rocket jet engine, Blue Origin's suborbital reusable spacecraft owned by Amazon's Jeff Bezos, and Richard Branson's Virgin Galactic.
The main rocket fuels are liquid, solid, and hybrid. Liquid fuels can be separated into petroleum, cryogenic, and hypergolic. Rocket fuel petroleum is highly refined kerosene called RP1. It's generally used in conjunction with liquid oxygen as the oxidizer. Operational lifetime is limited though, as kerosene burning engines produce a lot of residue. Cryogenic fuels are generally liquid hydrogen as the fuel and liquid oxygen as the oxidizer. They require low temperatures to remain in a liquid state, which means it's difficult to store them over long periods of time. They all have a low density as well, which means large storage tanks are required to contain it. Hypergolic fuels and oxidizers ignite spontaneously on contact with each other, so require no ignition source. It remains liquid at normal temperatures, but is highly toxic. Solid propellants motors burn until all their propellant is exhausted. Homogeneous propellants are typically nitrocellulose, which has both an oxidation and reduction capacity. They do not produce traceable fumes, which means it has great military applications. They are generally used to separate one stage from another. Composite solid propellants generally use aluminium as a fuel and the mineral salt as an oxidizer. They are usually held together by a polymeric binder, which is also consumed as a fuel. For high propellants, the fuel is usually a solid and the oxidizer is usually a liquid. The liquid is injected into the solid, whose fuel reservoir also serves as a combustion chamber. Hybrids are rarely used due to the difficulty of using them for very large thrusts.
Ion thrusters ionize propellant by adding or removing electrons to produce ions. Most thrusters ionize propellant by electron bombardment. A high-energy electron collides with a propellant atom, releasing electrons from the propellant atom and resulting in a positively charged ion. The gas produced consists of positive ions and negative electrons in proportions that result in no overall electric charge, called plasma. Neutral propellant is injected into the discharge chamber, where the electrons bombard the propellant to produce positively charged ions and release more electrons. High-strength magnets prevent electrons from freely reaching the discharge channel walls. This lengthens the time that electrons reside in the discharge chamber and increases the probability of an ionizing event. The positively charged ions migrate toward grids that contain thousands of very precisely aligned holes at the aft end of the ion thruster. As ions pass between the grids, they are accelerated toward a negatively charged electrode to very high speeds. The positively charged ions are accelerated out of the thruster as an ion beam, which produces thrust. The neutralizer expels an equal number of electrons to make the total charge of the exhaust system neutral. Without a neutralizer, the spacecraft would build up negative charge, and eventually ions would be drawn back to the spacecraft, reducing thrust and causing spacecraft erosion. The primary parts of an ion propulsion system are the ion thruster, power processing unit, and digital control and interface unit. The PPU converts the electrical power from a power source into the voltages needed for the hollow cathodes to operate, to bias the grids, and to provide the currents needed to produce the ion beam. The DCU controls and monitors system performance and performs communication functions with the spacecraft computer. A space elevator made of a carbon nanotubes composite ribbon anchored to an offshore sea platform would stretch to a small counterweight, approximately 62,000 miles into space. The counterweight spins around the Earth, keeping the cable straight and allowing mechanical lifters to ride up and down, carrying cargo and humans into space. The railgun space launch process is more complex than a rocket launch, but engineers say it's also more flexible. With it, NASA could orbit a 10,000-pound satellite one day and send a manned ship toward the moon on the next, on a fraction of the propellant used by today's rockets. It may seem far-fetched, but unlike other rocketless plans for space entry, each relevant technology is advanced enough that tests could take place in 5 years. NASA's scramjets have hit Mach 10 for 12 seconds, and railguns are coming along too. A 240,000 horsepower linear motor converts 180 megawatts into an electromagnetic force that propels a scramjet carrying a spacecraft down a 2-mile long track. The Craft accelerates from 0 to 1,100 miles per hour in under 60 seconds. Fast, but at less than 3 Gs it is safe for manned flight. The pilot fires a high-speed turbojet and launches from the track. Once the craft hits Mach 4, the air flowing through the jet intake is fast enough that it compresses, heats to 3,000 Fahrenheit, and ignites hydrogen in the combustion chamber, producing tens of thousands of pounds of thrust. At an altitude of 200,000 feet, there isn't enough air for the scramjet, now traveling at Mach 10, to generate thrust. Here space flight begins. The two craft separate, and the scramjet pitches downward to get out of the way as the upper spacecraft fires tail rockets that shoot it into orbit. The scramjet slows and uses its turbojets to fly back to Earth for a runway landing. Once the spacecraft delivers its payload into orbit, it re-enters the atmosphere and glides back to the launch site. The two craft can be ready for another mission within 24 hours of landing.